Right. So this video is about how to approximate expressions that are approximatable. That is, you might find a method to actually approximate them. And I'm going to show you some methods that can be applied in some cases. And yeah, let's start. So first thing that we want to approximate is the fourth root of 82. So the way I do this is that I can write that as the fourth root of 81 plus 1, which can be written as 3 times the fourth root of 1 plus 1 upon 81, which using the general binomial theorem can be written as 3 times of 1 plus 1 upon 4 times 81 plus, now the next thing is going to be 1/4 and then negative 3/4, so 3 upon 16, but that thing upon 2 is like 3 upon 32, so negative 3 upon 32 times 81 squared, right, this thing, and so on. So that's the way I can approximate this thing. Now as you can see, this is a really big quantity, so this whole thing is very small, and similarly all the terms after this, those will be really small. So these three terms must be sufficient for a good approximation. So you got 3 plus 1 upon 4 times 27 basically, and then minus so it's 9 over there, it's supposed to be 1 upon 32 times 9 times 81, I guess, right? So 3 plus 1 upon, so you got 8 and 28, so 108, I guess, right, minus 1 upon, so this thing, let's figure it out. So 9 times of it, like that's 729, of course, and that times of 32, it's gonna be 8, 1 carried on, you got 4 5, and then 1 4, and then 0, you got 7. Is that right or not? It is 0, you got 7, 2 carried on, 6, and then you got 8, and then 2 1, 8 2, 1 carried on, 5 3 1. So this thing 2 3 3 2 8, whatever that is, right? Yeah, so this thing is approximately 1 upon 100, so you can see it's 3.01, and then minus whatever this thing is, which, yeah, like what is this thing? It's really small actually, so I guess 3.01 is a good approximation. And now the real answer is 3.0092167 something, right? So approximately that much, actually 9 3.00, right, the actual answer is 3.0092116 and something in front of that, whatever. But as you can see, this is actually good enough because, yeah, I mean, it's 2 decimal places and it's close to that. So if you round this off, it's going to become 3.01. So yes, it's very close to that. So that's the way we can approximate this. Okay, that's awesome. So just gonna write that down. This is approximately 3.01. Okay, next, natural log of 1.1. How do we approximate that? So to do that, we can use the Taylor series natural log of 1 plus x, which is just going to be x minus x square upon 2 plus x cube upon 3, and so on. So whenever you will put 0.1 in this thing, you will get natural log of 1.1. So you just have to figure out what this series is, right? It's going to be 0.1 minus 0.01 upon 2, which is 0.005, I guess. Yeah, and then you got 0.001 upon 3, that's supposed to be 0.00 and 0333, whatever. So only these three terms are sufficient because other terms, why even include them, right? But you can, of course, you can say it's going to be 0.000 and then once again it's no, okay, just these much, and then that one upon 4. So for that, this would just become 0.25 or something, so 0 point that, and just keep on going. It's going to be negative, right? When you subtract, just get like 0.000, and you got 3 over there, and you got 1, and then oh, so that's gone, right? It's 0 and 8 and 333, whatever. This is good enough, I guess, right? So you got 0.1 minus 0.005 and then plus 0.0003, right? That's good enough. So you got 0 point, so it's gonna be 5 over here, it's 9 and 9 like that, yep. And then you got plus 0.0003, so 0.9953, I guess that should be good. And what's the actual answer? So the actual answer is 0.09531. Wait, is that correct or not? I mean, I did put 0. Wait, where did that extra? Huh, that's weird. They are saying natural log of 1.1 is 0.09531. I must have done something else in that case. But yeah, this is what I got after this approximation, right? Okay. Did I mess up somewhere? I mean, no, we know that 1 minus x plus x square, all of that stuff, that combined is just 1 upon 1 plus x, and then you integrate and you get this thing, right? When you put x equal to 0, this goes to 0, this goes to 0. So it's a correct thing. And then you can do this thing, right? Sure. So yeah, it's close to 0. Oh, okay, that's negative. How did I not see that? Okay, this is not here actually. It's just 0 right here. It should be 0. That's why. Okay, some silly mistake. Fine. Yeah, so 0.1 minus that's going to be this much, right? Okay, so 0.0953. Well, yeah, that's actually very close, because what they are saying is approximately 0.09531. And if I take these into consideration, this might have just become 1. So that makes sense, right? It's actually really close. So yeah, this is good. Approximately 0.0953. Okay, next. And then you got e power 0.1. So once again, another Taylor series. E power x can be written as 1 plus x square upon 2 factorial. But yeah, basically 2 plus x cube upon 6, because 3 factorial, and so on, right? So now you just put 0.1 over here. It's going to be 1 plus 0.1 plus 0.01 upon 2, which is 0.005. And then this time 0.1 is like 0.0005, but that thing upon 3. So yeah, 1, and then you got, for 20 just need 6, and yeah, so on, right? That's good enough. So just start adding. It's only 1.105166, well, whatever, right? Some stuff after that. So 1.1, and the given answer is 1.10517. So yeah, I mean, this would actually round out to be this thing, right? And there are actually more terms than that, so it's expected it's going to be slightly bigger than what we got. So yeah, that's how it's supposed to be. 1.10517, that's what it approximately is. So you see, these two series actually, I mean, they converged really fast. And this one, not so easy to calculate, but I mean, what other method you have? You can of course do square roots 2 times, but why would you want to do that? That's just painful, isn't it? Okay, and then you got 2 power 1 upon 7. So for this, I'm using a method that, it might feel like it's cheating, but I don't think it's like that, because it's not hard to remember the value of natural log 2. Natural log 2 is not that, I mean, uncommon a number to use, because it's used everywhere, I think. So natural log of 2, it's 0.693, but I'll just say it's approximately 0.7. Why I'm saying that? Because you got 1 upon 7 over here. So the thing is, I'm going to write this as e power natural log 2 upon 7, but then this stuff just becomes e power 0.1, which means actually this is the same thing as that. And let's see what the actual value is. So the actual value is 1.104. So yeah, you can see why this actually turned out to be like that. So this is approximately 1.1, that is, right? There's this, yeah, okay, instead of 5 you got 4 over here, but you get the idea, right? That pretty much the same stuff. And you could have gone for e power, okay, so 0.693 and that thing upon 7, right? Yeah, which I can think is, it's like, okay, 0.1, and then you got 0.7 minus this guy, and all of that upon 7, right? Okay, so you got 1 minus, so what would this be? You got 6, and then that's going to be 0, and oops, it's supposed to be 7 right here. Okay, 7, that's going to be 0, and then that's going to be 3, and yeah, right. Okay, no, that's 7 over here. Okay, that's supposed to be 0. So 0.007, okay, that plus this, of course, that becomes 0.7. So it's 0.7 minus that much. And yeah, okay, that upon, yeah, I mean, just write it like that, 0.7 minus 0.007. And then all of that thing upon, um, right, upon 7 basically, right? That's going to be equal to 0.1 minus 0.001. So yeah, um, e power all of that, e power 0.1 we already know is just 1.1051. Well, what do we get? uh, hey, wasn't this 1? I don't know how that turned out. Weird thing. Okay, I got 7 over it. Fine, let's say it's 1.10. I guess that was 1 and not 7. I don't know, maybe it was. No, it can't be. Yeah, it was 1 not 7. Right, so 0 point, yeah, this is the actual value. So this thing, 1.10517, that's what e power 0.1 is. But then that upon e power 0.001 whatever, if you think about it, um, right, I mean, it's just like, isn't it like the 10th root of this? Okay, whatever, just skip that. You have to actually figure this out. I mean, this is so small, right? This value is just so small that even the first term would be enough. So you got 1 minus 0.001. That's enough, in fact, because the next term is going to be so small. Just forget about that. So you got 1.10517 and then minus, 10 power negative 3 of this guy. So where's that going to be? 1, 2, 3, okay, 1 and then 1 over here. 0517. Is that the case? I mean, 1, 2, 3. Yeah, okay, that's the thing. So this is approximately this much. So we're gonna have 7040111, and I can see why that 4 is here, because of this extra term. So that makes sense. Okay, so the more accuracy you put over here, the better will the result be. And by the way, this actually matters a lot because exponential functions grow really fast. So this must be really accurate, and then you'll get a good answer. But if you don't want that much of accuracy, you can just go for something less accurate. It will still work, just with less accuracy. Okay, so that's done. I mean, this is approximately 1.104, right? That's what we got. What about 7 power 2 upon 5? So this is, you might say, okay, you can do the same thing over here, right? E power 2 upon 5 natural log of 7. But the thing is, natural log of 7 is in fact uncommon. Natural log of 2 not so much, but people don't know what natural log of 7 is. In fact, I at this point too don't know what natural log 7 is, so we won't use this thing, right? So what other method do we have to do this? Some other kind of Taylor series? No. The thing is, I will use another method to solve this. So other than Taylor series, that is, I will use Newton's method. So yeah, the thing is, we'll just set this thing to be equal to x, and then you can form an equation, a polynomial equation involving only integer coefficients, and this is the thing, right? Okay, that looks cool. We'll call this left hand side as f of x, and first thing we'll figure out is g of x, which is f dash of x upon f of x. You will see why I'm doing this later on. This is going to be equal to x power 5 minus 49 upon 5x power 4. Oops, 5x power 4. That's going to be 1/5 of x minus 49 upon x power 4, right? Okay. And now the thing is, I'm gonna explain what this actually is. Why do we need this? So the thing is, you got this function. If I graph it out, it's gonna look something like this. We want to find its 0 basically, right? So what I'm going to do is, just take a guess and see where it hits on the graph. So we'll just say this is x naught, and then I'm going to draw a tangent like that onto this point wherever it hits the graph, and I'll figure out what this point is. We'll call this x new, this is x old, and if I can figure out what x new is, that's a much better approximation than x old, right? And then I will do the same thing for x new and so on, and eventually I'll get to this point. Actually, I will never get to that point. I'll just get a really good approximation. Yeah. And the way to figure out xn is, of course, I mean, you just got the rise over run, so you got this thing that's going to be f of x naught upon this, so it's x naught minus xn. This slope is just equal to f dash of x naught, right? So that just means x naught minus xn is equal to f of x naught upon f dash of x naught, which means xn is equal to x naught minus f of x. Basically, this thing is just g of x naught, right? Yeah. So yeah, what's xn actually going to be equal to? So g of x naught is just this whole thing. So x naught minus that's going to be 1/5 of 4x plus 49 upon x power 4, right? Okay, that's awesome. And right, let's start off with some good guess. I mean, the closer the x naught is, the better will your answer be, right, for xn. So yeah. So what you got? You got x power 5 is equal to 49, right? So 2 power 5 is 32. It's, I mean, I would say it's close, but I don't think that's close enough. So, okay, 3 power 5 is straight up 243. Not nice. What about 2.1, or let's just say 2.2 power 5? So we can write that as 32 times 1 plus 0.1 power 5, which is approximately, maybe we shouldn't be doing that, but whatever. 32 times 1 plus 0.5, and that's like 32 plus 16, which is 48. It's actually more than that, I guess, right? But whatever. So I guess that's a good approx. Yeah, right. I guess we should start at 2.2 or 2.1 or something close to that, right? Yours, I mean, okay, let's go for some more accuracy and see if that is in fact a thing. So you're gonna have like 5 times 4 upon 2, so 10, and then that's gonna be squared. So like a, yeah, wait a second, that's the thing. And then you got 5 times 4 upon 2, is that right? So that's gonna be 10 times this, like that's gonna be 0.1, and okay, so that's just 0.6. So basically, like this thing plus 3.2, that's going to be 1.2 or something, in fact even more than that, right? So eventually, right, that's how it's going to be. I mean, it's just a normal binomial expansion, nothing so crazy, right? No negative exponent or whatever. So I guess that's understandable. And the next term is going to have 10 once again, right? That's the coefficient, but then you will actually have 0.1 cubed, so you got 0.01 or something. And the next one just has like 5 times of 0.1 power something 4, of course, which is small, so just ignore that, I guess. Yeah, so 1.2 is where it's gonna go. So 2.1 would be better, I don't know. I guess 2.2 is what we should be doing, because, right, yeah, I think we should be doing 2.2. Okay, so let's just put in 2.2 and see what we get into this formula. And usually this gives a really nice approximation without much problems, but we'll have to actually work that out by all that division, and yeah, that's problematic. But hey, just do this thing. So 2.2, that's what we'll put as x naught. So 4/5 of x naught, that's like 0.8 times 2.2, which is 176. Okay, 1.76, right, 1.76. And then you got this thing, so 49 upon 5 times of this guy power 4, right? Yeah, 2.2 power 4, it's like 2 power 4, and then you got, okay, we should not be doing that, I don't know. And then you got 1.1 power 4 or something, 4 power. So 49 upon 10 times 2 power 3, and times this stuff, 1.1 power 4. This isn't that hard. Actually, you know what? We should really be doing this thing. 1.1 times, so, okay, 1.1 to the power of -4, because that's a better approximation, rather than, dividing that. Yeah, that would be exact values, but not so easy. So this is easier. This is like, okay, 1 minus 0.4 and then negative 4, negative 5 upon 2 is like, that's only negative 10. So right, okay, actually positive 10, and that times 0.01, that's right, it's gonna be 0.1. Okay, and what else you got? 4 times 5 times 6 upon 2 times 3 in this case, so it's gonna be just 20, and then 20 times 10 power negative 3, I guess. So that's gonna be 2 times 10 power negative 2 is 0.02 in negative, of course, right? And it's gonna keep on going like that. Just one more, okay, times 7, and then you got 4 over here. That cancels, this cancels, you got 35 times 10 power negative 4 or something. It's going to be 0.0035, right, in positive. So you're getting that, right? Okay, that's enough. So this is negative 0.3, I guess. 1 minus 0.3, and you got this guy minus 0.32 basically, and you got approximately 0.003, because next term is going to be negative anyway, right? So might as well just approximate like that. So you got okay, what's this going to be? 0.68, and then you got this plus that, okay, 0.683, whatever that is. Still 0.7 is better, but hey, whatever. So that's this part, and then you actually have to do 49 and then all that stuff. Okay, 49 times 0.683 upon 10 times 2 power, like 10 times 8 basically, right? Okay, what I'm thinking is maybe we can just write this as 48 approximately. Nah, just do it the proper way. So it's 4.9 times this thing upon 8, it's like 0. So for 4 you're gonna need 0.08, and you got 43 huh? Okay, so 9, 36, and then you will need, so you got what, 70. Okay, so 70, for that you will need 8, so 8, 64, and then you will need 60. So for 60 you will need 7, 56, and then 40. So this is the thing, right? Yeah, so 4.9 times all of that stuff. You will actually have to deal with this. There's no, or you can just say it's 0.09, approximately that much. So wait, we can just make this larger and this thing small. Nah, just do this thing. Just remember that what we got is actually a little larger than what we actually should have got, right? So for the xn value, yeah, but keep going. So what is this going to be? We got 36 and 81, that is 441, right? So 441, and then how many of these? 3, so 0.441. Okay, so 0.441, right? That's the thing, I guess. Okay, when you combine, just get 2.2, I mean that's like that. Okay, that one is there, that's gonna come down, and then 0, 1. Oh, that's not so far away from 2.2. What's the answer though? So I guess 2.2 was a good guess, and the actual answer is 2.1779. So I guess what happened is that by doing all of this approximation, we probably ran into some errors, right? So okay, if we did this with more accuracy, so instead of saying it's 0.89 and something like that, if we actually did this, so right, I mean 0.09, is that not a good approximation by itself? I don't know, it should have been. Okay, let's do this other term correctly, right? Okay, so no need for all of this, right? I guess that's where the error is coming. This term is probably what's causing the error, because I mean usually it doesn't do that much when the calculations are simple. Maybe I just got a bad example or something. So 49, and then you got 10 power 4, right? So 3, yeah, and then you got this guy 5 times of 22 power 4 basically, right? Okay, so you got 4, 9, you can just do that thing, 000 pawn. So one of these 2's are just out. You got 11 times 22 power 3, Let's figure this out. 22 power 3, huh? Interesting. You can also think it's like 8 times of 11 power 4. 11 power 4 is like 14641, isn't it? 11 times of 8, that's going to be 8. And then you got 2 3 carried on. You got 48. 48 3 is like 1 5 carried on. 32 and 5 is 7, and 3 carried on, and then that's 1 1. So it's supposed to be 49000 upon 117128. That's quite a lot actually, right? So yeah, let's start doing it. 49000, and then you are dividing it by what number? Maybe we can actually first of all reduce this thing, so by 4, right? You want to have 1 and then 2, so 8, and then 10. So wow, that's taking so much longer than what I expected, right? And then 5 and 0 upon, so 2 8 37 9. Okay, we got 11, so 2 and then 8 and then 32 is 4 and 2, right? Okay, 2 once again, so 6 1 2 5 upon 1 and then 4 and then 12, so you need 6 and then 2 and 1, right? Okay, what is like 3 and then, okay, that's not a multiple of 3. Yeah, you probably shouldn't do that. 21 over here, 146, whatever, you just have to do it at this point. 6125, and you have to divide by 1. We want at least 2 decimal places, and the actual answer, yeah, okay, maybe 3 decimal places, but this only has 2 decimal places. Well, whatever, we'll see what we get. Got 6 over here, and then you got 14621. Okay, let's do it. So 0 point, and okay, so what about this times 5? No, too much. What about 4? So you got 4 4 8 4 2 carried on. Okay, it's supposed to be 56 or something. It's like 58. You got 6, and then 14 minus 8 is 6, and then 11 minus 4 is 7. 2, yeah, okay, 2 7. How many of these guys? Right, maybe just 2. No, 1 minus 1 4 6 2 1, so 9, and then 5 minus 2 is like 3, and that's 0, and that's 3, and that's 1. Okay, just one more decimal, so you got 130 something, right? 3 probably, no, okay, they got 1 4 or whatnot. 4 6 2 1, I mean that would have worked if this was, so maybe like 2 is better or something, I don't know. Okay, what about 9? No, this time's 9 is probably not good. 9, and then you got 36, that's 1 2. Okay, let's just try it out, maybe it won't be that bad. So 9 8 1 carried on, you got 54, and 1 is like 5 carried on, 36, and 5 is 41, 4 carried on, 9 and 4 is like, okay, 1 3, this thing. Oh, that's little too much, right? Maybe 8 is better. This thing with 8, it's gonna be 8 6 1 carried on, right? And then 48, so you got 9 4 carried on, you got 32, and 8 is 0 4 carried on, and then that's 8. So this thing, I know it's taking much longer than what I expected. Okay, 64, that's gonna be 9, right? This thing, so 14621 times what is close to that. This times 5 would give us 70 something, so maybe this times 6. This times 8 would 8 and 32, no, that is too much. 6 is probably the way to go. So minus, you got 6 and then 2 1 carried on, 36, and okay, that's supposed to be 7, and then 3 carried on, so 6. Okay, 3 carried on over here, right? And then 24 and 3 is 7 2 carried on. Okay, this thing, yeah, it's good enough. So this is what we get approximately. Just put that in there. So plus 0.4186, and then when you add these up, it's, what is this? So 1.76 plus that guy, what, 6 8 7 1, you got 2.1786. and the real answer is 2.1779. So I guess that's, I mean, close enough, right? Yeah. So yeah, uh 2.18 or something, that's how we'll round it off. So it's approximately 2.18, right? Okay. And by the way, if you got one unsure digit over here, after doing this step, you'll just get uh you know right, you'll just get two more decimals. Okay, what am I saying? Your the unsure digit will shift basically, right? What am I saying? I just can't express it very well. But the thing is, okay, over here you got an error of plus minus 0.1. Over here you got an error of plus minus 0.01, right? So you got an extra decimal place basically. Thing is, like, this one became two times, if that makes sense, right? Okay. So yeah, and that's it. So I'll see you guys in the next video. Yeah, it's approximately 2.18.